Hey the. Hello. In this video, we will discuss Hadamard consistency. Specifically, we will represent consistency constraints by using dynamic programming within Hadamard Butterflies. The consistency problem is defined like this. We are given a number of decisions D, a set of constraints C, and a number of truths T. A consistency algorithm must find a vector of decisions of length D that meets the constraint C and that has T truths. Constraints of the form constraint ij mean that decision I and decision j may not both be true. Either decision I or decision j, or both, must be false. Constraints of the form constraint I mean that decision I must not be true. Let's review the Hadamard population theorem. For all vectors v and w, the dot product of the fast Hadamard transform of v with the fast Hadamard transform of w is equal to n times the population of v intersect w. V and w are binary vectors of length n. FHT of x is the fast Hadamard transform of vector x. Note that we could just say Hadamard transform, because Hadamard transforms and fast Hadamard transforms compute the same thing. However, we use the fast Hadamard transform butterfly as a key part of the algorithm, and so we use the word fast deliberately. Pop of x is the population of vector x. The dot is the dot product of two vectors. And means the element-wise and of two vectors. And the size of the vectors n must be a power of 2. Note that we prove this theorem in another video in this series. Also note that this theorem is remarkably similar to convolution. Here's an example. Let's say that v is the vector 1, 0, 1, 1, and w is the vector 1, 1, 1, 0. In this case, the length of both vectors is 4. On the fast Hadamard transform side, we have the fast Hadamard transform of v dot product the fast Hadamard transform of w. First, we substitute v and w into the expressions to get the fast Hadamard transform of 1, 0, 1, 1 dot product with the fast Hadamard transform of 1, 1, 1, 0. Then we compute the fast Hadamard transform of both vectors to get 3, 1, minus 1, 1 dot product with 3, 1, 1, minus 1. And computing the dot product gives us 8. On the population side, we have the expression n times the population of v intersect w. We substitute n, v, and w into the expression to get 4 times the population of 1, 0, 1, 1 intersect 1, 1, 1, 0. Computing the element-wise intersection gives us 1, 0, 1, 0. The population of that is 2, and simplifying gives us 8. So we can compute the results either way. We will use the Hadamard population theorem to map consistency constraints onto fast Hadamard transforms. We are concerned mainly with vectors that have 1 or 2 bit set. Vij denotes the binary vector with only bits I and j set to true. I must differ from j. Vi denotes the binary vector with only bit I set to true. For binary constraints, the fast Hadamard transform of Vij dot product the fast Hadamard transform of any binary vector w must be in the set 0, n, and 2n. This is because the element-wise intersection of Vij with any binary vector w must contain 0, 1, or 2 bits. And if we have a constraint that both bits I and j may not be true, then the fast Hadamard transform of Vij dot product the fast Hadamard transform of w must be in the set 0, n. For unary constraints, the fast Hadamard transform of Vi dot product the fast Hadamard transform of any binary vector w must be in the set 0, n. This is because the element-wise intersection of Vi with any binary vector w must contain 0 or 1 bits. If we have a constraint that bit I must be false, then the dot product of the fast Hadamard transform of Vi with the fast Hadamard transform of any vector must be in the set 0. So if we look at the definition of consistency, we want to find a binary vector W where the length of W equals the number of decisions. For all constraints of the form constraint ij, we will require that the fast Hadamard transform of Vij dot product the fast Hadamard transform of W is in the set 0n. For all constraints of the form constraint I, we will require that the fast Hadamard transform of Vi dot product the fast Hadamard transform of W be in the set 0. And finally, the population of W must equal the number of trues. Here's an example. Supposing we want to find 4 decisions, we have 4 constraints. Bit 0 and bit 1 may not both be true. Bit 0 and bit 2 may not both be true. Bit 0 and bit 3 may not both be true. And bit 3 may not be true. And the number of trues we're looking for is 2. The constraint 0, 1 corresponds to the vector 1, 1, 0, 0. The constraint 0, 2 corresponds to the vector 1, 0, 1, 0. The constraint 0, 3 corresponds to the vector 1, 0, 0, 1. And the constraint 3 corresponds to the vector 0, 0, 0, 1. The fast Hadamard transforms of those vectors are respectively 2, 0, 2, 0, 2, 2, 0, 0, 2, 0, 0, 2, and 1, minus 1, minus 1, 1. For the first 3 constraints, the dot product must equal 0 or 4. For the 4th constraint, the dot product must equal 0. So we will map those constraints into the following equations. 2 times A plus 0B plus 2C plus 0D must be in the set 0, 4. 2A plus 2B plus 0C plus 0D must be in the set 0, 4. 2A plus 0B plus 0C plus 2D must be in the set 0, 4. And 1A minus 1B minus 1C plus 1D must be in the set 0. Our goal is to find a vector W where the fast Hadamard transform of W equals the vector A, B, C, D. The value A corresponds to a population cell, so A must equal the number of trues. Here's an example solution to that. If the fast Hadamard transform of W equals 2, 0, 0, minus 2, then we have a solution. W will be the inverse fast Hadamard transform of 2, 0, 0, minus 2, which equals 0, 1, 1, 0. 0, 1, 1, 0 matches all of the constraints. Bit 0 and bit 1 are not both true. Bit 0 and bit 2 are not both true. Bit 0 and bit 3 are not both true. And bit 3 is not true. And we have 2 trues. And to show how this works, we substitute the values 2, 0, 0, and minus 2 in for A, B, C, and D. And note that in each case they simplify to true. In many ways, this looks like integer programming. However, the Hadamard butterflies give us structure so that we can solve the equations efficiently.
Note that the algorithm is not particularly fast. By efficiently, we mean in polynomial time.
The representations we will use differ a little bit from the classic butterfly. On the left of this diagram, we show a classic Hadamard butterfly for a vector of size 4. First, we will transpose the butterfly so that the left column appears across the top and the right column appears across the bottom. It's otherwise identical. The main reason for transposing is to open up space in the diagram in order to express all of the information that we need. The next thing we want to do is to distinguish between population nodes and non-population nodes. Population nodes only have positive inputs, or solid lines. Non-population nodes have at least one negative input, or dashed line. In this diagram, the blue nodes are population nodes, and the white nodes are non-population nodes. The domain of population nodes is always 0 to 2 to the t, where t is the tier. The domain of all non-population nodes is minus 2 to the t minus 1 to positive 2 to the t minus 1. In this case, t is the distance from the top tier. In this diagram, the top tier is tier 0, the next tier is tier 1, and the bottom tier is tier 2. The next change we will make is to reverse the arrows. When the arrows go from top to bottom, it shows the flow of information through a Hadamard transform. We're going to reverse the arrows because we're going to do dynamic programming within the Hadamard structure, and we're going to go from bottom to top. All nodes within a butterfly contain sets of records that contain a Hadamard value and a partial sum value called a pair. The Hadamard value is the actual Hadamard value for that node. The partial sum value is the sum of the equation represented by the nodes below. We denote these pairs using colons or angle brackets. The Hadamard value is derived from the fast Hadamard transform of the solution vector. The partial sum value is derived from adding together terms of the dot product of the fast Hadamard transform of a solution vector with the fast Hadamard transform of a constraint vector. If we have valid pairs for two child nodes, then we can create valid pairs for two parent nodes. The left child pair will be denoted H0PS0, and the right child pair will be denoted H1PS1. In the left parent node, the Hadamard value will be H0 plus H1 divided by 2, and the partial sum value will be PS0 plus PS1. In the right parent node, the Hadamard value will become H0 minus H1 divided by 2, and the partial sum value will be the partial sum 0 plus partial sum 1. As expressed in our video on the properties of fast Hadamard transforms, there are constraints on which child pairs may be combined together. The first rule is that H0 and H1 must have the same parity. The second rule is that the parent Hadamard values must fit within the Hadamard domain of the parent nodes. There are cases where H0 plus H1 divided by 2 or H0 minus H1 divided by 2 lie outside of valid parent domains. We now have enough information to represent constraint equations in terms of butterflies. We will use an entire Hadamard butterfly to represent each equation.
The nodes throughout the entire butterfly express the partial sums of the equation. This particular butterfly will represent the equation 2 times A plus 0 times B plus 0 times C plus 2 times D must be in the set 0, 4. First, we will fill the butterfly with all potentially valid equation pairs.
The leaves of the butterfly express the terms of the equation. The bottom left node corresponds to the A term, the node next to that corresponds to the B term, the node next to that corresponds to the C term, and the final node corresponds to the D term.
In the middle level, nodes E and G express the partial sums of nodes A and C. Nodes F and H express the partial sums of nodes B and D. At the top level, nodes W0 and W1 express the partial sums of nodes E and F, and nodes W2 and W3 express the partial sums of nodes G and H. Also note that the nodes at the top level express the total sum of the entire equation, which must be either 0 or 4.
The Hadamard domain of node A is 0 to 4, but only one value will work because the population must be 2, so the Hadamard value must be 2. So the partial sum will be 4, which is 2 times 2. The Hadamard values for node B range from -2 to +2.
Since we don't yet know which Hadamard value will be selected, we must consider them all.
The partial sum, which equals 0 times B, will always be 0 regardless. In node C, the Hadamard values range from -2 to +2.
Again, we don't know which Hadamard value will be selected, so we must consider them all.
And once again, the partial sum for this node is equal to 0 because the partial sum equals 0 times the Hadamard value. And in node D, the partial sum will be 2 times the Hadamard value. The Hadamard value for node D ranges from -2 to +2.
And we still don't know which Hadamard value will be selected, so we must consider them all.
And so the partial sum ranges from -4 to +4 by 2's.
To compute all valid equation pairs for parent nodes, we try all combinations of valid equation pairs from the children within the Hadamard butterfly. In order to get all of the valid states for node E, we are going to consider all combinations of equation pairs from node A with equation pairs from node C. Node E is a left node, so the Hadamard values will be added. Node A has one valid equation pair, which is 2, 4. Node C has 5 valid equation pairs, as shown. First, we try combining the 2, 4 with minus 2, 0. To get the Hadamard value, we add 2 and minus 2, and then divide by 2 to get 0. To get the partial sum value, we add 4 plus 0 and get 4. Then we try to combine 2, 4 with minus 1, 0. We note that the Hadamard values of 2 and minus 1 have different parities, so these equation pairs cannot be combined. Then we try to combine 2, 4 with 0, 0. To get the new Hadamard value, 2 plus 0 divided by 2 equals 1, and the partial sum is 4 plus 0. Then we try to combine 2, 4 with 1, 0. The Hadamard values of 2 and 1 have different parities, so we cannot combine these equation pairs. And finally, we try to combine 2, 4 with 2, 0. The Hadamard value will be 2 plus 2 divided by 2, which equals 2, and the partial sum value will equal 4 plus 0, which equals 4. So node E has these 3 valid equation pairs. We proceed filling all of the nodes in the middle tier. We'd like to comment on filling node H. Node H is a right node, so the Hadamard values will be subtracted. When we combine the equation pair minus 2, 0 from node B with the equation pair 0, 0 from node D, the Hadamard value will be minus 2 minus 0 divided by 2, which equals minus 1. And the partial sum will be 0 plus 0, which equals 0. That computes one equation pair in node H. Consider combining minus 2, 0 from node B with 1, 2 from node D. The Hadamard values, minus 2 and 1, have opposite parities, so these two equation pairs cannot be combined. Then we try to combine the equation pairs minus 2, 0 from node B and 2, 4 from node D. The Hadamard value will be minus 2 divided by 2, which equals minus 2. But that lies outside of the Hadamard domain of node H, which goes from minus 1 to 1. So these two equation pairs cannot be combined. In the top tier, W0 is a left node, so we will add the Hadamard values. So when we combine these equation pairs, the Hadamard value will be 2 plus 0 divided by 2, which equals 1. And the partial sums will be 4 plus minus 4, 4 plus minus 2, 4 plus 0, 4 plus 2, and 4 plus 4, which gives us 0, 2, 4, 6, and 8. We will also try to combine these equation pairs. The Hadamard value of the parent will be 1 plus 1 divided by 2, which equals 1. The partial sums will be 4 plus 0, 4 plus 2, and 4 plus 4, which will give us 4, 6, and 8. In node W0, the equation pairs 1, 4, 1, 6, and 1, 8 can be computed in two different ways. We note that on the bottom tier, all equation pairs can be computed in exactly one way. On the next tier up, in general, some equation pairs can be computed in exactly one way, while other equation pairs can be computed in multiple ways. Above the second tier from the bottom, most equation pairs can be computed in multiple ways. We continue filling nodes in the top tier. We note that node W3 is a right-hand node, so we will subtract the Hadamard values. When filling node W3, we will consider these equation pairs. The Hadamard value is 1 minus 1 divided by 2 equals 0. The partial sums will be 4 plus minus 4, 4 plus minus 2, and 4 plus 0, giving us 0, 2, and 4. We will also consider these pairs of equation pairs.
the Hadamard 0 minus 0 divided by 2 equals 0. The partial sums will be 4 plus minus 4, 4 plus minus 2, 4 plus 0, 4 plus 2, and 4 plus 4, giving us the 0, 2, 4, 6, and 8. We note that most of those equation pairs can be computed in multiple ways. By combining all of the different valid equation pairs in the middle tier, we can compute all of the valid equation pairs for the top tier. Notice in this case there are a lot of equation pairs in the top tier. We have successfully filled the equation butterfly. Now we notice that the constraint equation requires that the total sum be in the set 0, 4, which means that W0, W1, W2, and W3 must have partial sums that are in the set 0, 4, which means that many values in those nodes are not valid. In particular, the partial sums 2, 6, and 8 are not in that set, so we will delete them. And this gives us the filled equation butterfly. Now we are going to demonstrate a process we call ringing the butterfly. We are going to remove all equation pairs that do not participate in valid total sums. First step in ringing is to remove all equation pairs from the middle tier that do not contribute to valid equation pairs in the top tier. So in node F, the equation pair minus 1 minus 2 cannot be combined with any equation pair in node E to produce equation pairs for nodes W0 or W1, and so on for the other partial sums marked in red. Likewise, in node H, the equation pair 0, 4 cannot be combined with any equation pair in node G to produce equation pairs in nodes W2 or W3. All of the equation pairs marked in red do not contribute to any valid equation pair in the top tier. Removing all invalid equation pairs from the middle tier results in this butterfly. And finally, we will consider deriving all of the equation pairs in the middle tier from the bottom tier. The partial sums marked in red do not contribute to any valid equation pairs in the middle tier. So those partial sums will be removed, leaving this constraint butterfly. That shows how to strip nodes down. The next step is to strip nodes up, which involves ensuring that every equation pair in the middle tier can be derived from equation pairs in the bottom tier, and then ensuring that every equation pair in the top tier can be derived from equation pairs in the middle tier. This particular butterfly does not change when we ring up. However, in general, ringing will involve stripping down and then stripping up multiple times. The fixed point is the minimal butterfly from which no additional equation pairs can be removed. This butterfly embodies all solutions to the constraint equation, even though they are diffuse and scattered throughout the butterfly. Now we are going to view the code that underlies this entire algorithm. We will only sketch it out here because the code will be available online. Position objects identify the specific properties of each butterfly node. Specifically, the position tells us whether the node is a left node or a right node, and the Hadamard domain. We also store the tier and the term just for clarity. The position nodes also support two operations. The first computes whether two child Hadamard values could be combined to make a valid parent Hadamard value for this node. The second combines two child Hadamard values to create an actual parent Hadamard value for this node. These operations are tied to position because they depend on whether the node is a left node or a right node and what the Hadamard domain actually is. Equation pair states contain two values, a Hadamard value and a partial sum value. There are two kinds of equation nodes, leaf nodes and parent nodes. All equation nodes have a position and a set of valid equation pairs. Parent nodes also have left and right children. Leaf nodes do not. These are the main equation node operations. The first constructor creates a leaf. The second constructor creates a parent node with two children. Fill leaf adds all possible equation pairs into a leaf based on the constraint multiplier.
Fill parent adds all possible equation pairs into a node based on its two children. Assign Hadamard removes all equation pairs that do not match the specified Hadamard value. Assign partial sums removes all equation pairs that do not match the specified partial sums. Strip up to parent is used in ring, and it removes all parent equation pairs that cannot be derived from valid children equation pairs. Strip down to children is used in ring, and it removes all equation pairs from children that do not contribute to a valid parent equation pair. And the number of valid pairs is used by ring to determine whether anything changes in the butterfly to determine whether ring should keep going. The equation butterfly state really has a two-dimensional array of nodes. However, we also store the number of tiers and the number of terms for clarity. There are two main butterfly operations besides the constructor. The first fills a butterfly with all of the data associated with the specific constraint, and the ring function removes all equation pairs that could not be valid given what is known. A quick note on complexity. We stated that the algorithm is polynomial, and here are the complexities of the operations involved. The size of each equation pair is O1. It consists of a Hadamard value and a partial sum value. The size of each node corresponds to the number of pairs per node. Consider the domains of the Hadamard values and the partial sum values of nodes in the bottom tier. There are n+1 possible Hadamard values. Since the partial sum value is a constant between -2 and 2 times the Hadamard value, there are O of n partial sum values. If we combine the two, there are O(n)² combinations of Hadamard values and partial sum values. When we go up a tier, the number of Hadamard values is cut in half, but the number of partial sum values is doubled. And so every node in the next tier up has O(n)² combinations of Hadamard values and partial sum values. And this pattern continues all the way to the top. So every node in the butterfly has at most O(n)² equation pairs. The number of nodes per butterfly is n log n. So the size of each butterfly in terms of number of pairs per butterfly is n³ log n. The number of steps per node that it takes to fill up a node, strip up a node, or strip down a node is O(n)⁴. Both children may have n² valid equation pairs, and the parent must consider all combinations, which is possibly O(n)⁴ valid equation pairs. The number of steps per butterfly to fill or strip up or strip down is the number of steps per node times the number of nodes, which is O(n)⁵ log n. The number of strip-ups and strip-downs per ring is an open question at the moment. We know that it is at worst O(n). However, we believe that it is actually at worst O log n. So the total number of steps per butterfly for a make or a ring is O(n)⁵ log² of n. In the next video, we will discuss how to merge all of the constraint butterflies together and then extract a result.